My name's Jeff Reback. I work at 2 Sigma now. I've had a career working in a number of different places. I actually worked at Continuum for a little while. And I've been managing pandas since about 2013. It's been pretty interesting. I started off as an occasional committer, or actually back then it really wasn't even, we didn't use too much GitHub. It was just more like, oh, there's like some issues. GitHub was in its infancy back then, and eventually it's like a trade. You start trading the project and then you start owning it. So I start off my slide decks usually this is Wes McKinney. He is the original owner of the project. He gets all the kudos. I get all the complaints. Okay, thank you. All right, so before we talk about InterJNA, we're going to talk about the state of pandas, and this will lead you to see where we are. So the good about pandas. Then we're going to talk about the current state of pandas. Hopefully we can turn into this. So it's a happy panda if it doesn't look good there. Yeah, I mean, pandas is pretty heavily used, but people are starting to run into some of the limits, and we'll talk about that during this talk. All right, so some of the good things. Python's pretty popular. This is like a good thing. You've probably all seen this chart. This is the Stack Overflow questions that have occurred over the last few years, and you can see Python has an amazing trajectory here. It could also be that Python is just getting harder, or I think it's more that we have a lot of newcomers who are using the languages, and of course they have questions. And Stack Overflow is now pretty much the place to use these. Oop. There. So one of the big drivers has been the data science stack. It used to be you'd go to PyCon and you could call it DjangoCon. But actually, last couple years have been really data science at the forefront, and this, of course, has been driving a lot of the tooling, things like Conda and Conda Forge, and of course, a lot of the packages that anchor the data science stack, like NumPy and Matplotlib and pandas. And so you see the popularity here. I don't know whether this is causal or not, but. Now, I'll point out one thing, which is, let's see if I can see I don't have a mouse here. I'll point out. So I started managing the project in 2012, so. So just an overview of where pandas, where I view it sits, but pandas is essentially the user API for data science. You're bringing in your data, via pandas, and in fact, probably the biggest success of pandas has been the CSV reader. It has brought a lot of people their data in and done some minimal cleaning on it. And then of course what you do is you can dispatch to other packages, scikit-learn and TensorFlow and all the fancy packages out there, or even basic statistics like stats models have been very, very popular and used, and pandas just works pretty well with them. Scikit-learn actually just released a new version which works, to preserve your column labels, which is always nice. And of course, then you want to visualize your data, and so pandas has some easy to use dispatch mechanisms to Matplotlib and things like that. So pandas sort of sits at the nexus of the whole data science stack, and this has been great actually. It means pandas is used pretty heavily, so we've seen lots of feature requests and enhancements and bug reports, of course. So this leads me to the bad and the ugly. Pandas has been, we'll say it's showing its age. Pandas has really been around since about 2008. That's when it was originally set up. And of course, back then, what did you do? You always started with a 2D NumPy array of floats. That's what you did. Why? Because that was easy. That's what you had already. But the landscape is changing a lot. Now, most data you're getting from maybe a remote data source, or maybe you're even reading it off disk, but you're reading a certain smaller number of columns. They potentially have and usually have multiple dtypes. So it's a little bit harder to manipulate this data, and especially as things scale. And that's where people are starting to hit limits. We're not going to talk about these warts in pandas today, but I'm just listing a couple of things that I particularly find limiting. Complex group eyes get hard to express. In some sense, this is a fundamental limitation of Python itself. We don't have macros, but that's just an issue. UDFs, which is user-defined functions, they're very opaque to pandas. In other words, everybody's done a group by apply, and then it's slow, and you wonder why. Well, because we can't delve down into the code you're using. Now, there's a lot of ways to work around this and things like that. And of course, the big problem is copy semantics are very awkward in pandas. We basically copy everything. The data frame is mostly immutable, and this causes memory blowup. So I have a slide in a second about this, but this causes problems for performance. And this is, of course, when you scale. Furthermore, pandas is not really a first-class citizen in terms of the data science world when we want to share data. It's great when you're in Python, but if you want to share with like Julia or with R, it's increasingly become hard. Now, there are some solutions on the horizon. Pandas integrates a lot better nowadays with PyArrow, which does have cross-language interop. So this is definitely improving. So this is the state of the world right now. Pandas is fantastic, really up to like 10 gigs or something. And of course, you can get really big machines nowadays, but it still becomes hard. So the question is can pandas change to accommodate some of these even larger use cases? And the answer is I think we can do some things. So one thing that is happening is the increasing adoption. We're using it more internally of PyArrow. We're using it to read Parquet. We're also using it to do data interchange. This helps to unify the pandas when it's used in big data type environments like Spark, things like that. But I think we can do even more. And this is the point of this talk here today. So I would say about 6 or 8 months ago, there was a use case which I'm going to go over where we needed, well, let me back up a little bit. Over the years, we've had NumPy as our base memory format and our dtype system. And a few years ago, this became relatively limiting. We wanted to do things like have datetimes with time zones. We wanted to have categorical dtypes. And this was increasingly hard to do. Well, we made things work, and it was just not, it solved a lot of issues. But it wasn't general enough, or it wasn't flexible enough to handle even more things out there. Our dtypes were, ad hoc. Every time we wanted to add something, so we started off with datetimes with time zones and categoricals, and we eventually added some support for intervals and some support for periods as first-class types in data frames. But they were a lot of effort to implement these. They were a lot of work. So Tom Augsburger, and he defined the first standard for this. We call it extension arrays. This is we'll call it an interface specification for how to add external both dtypes and memory formats and computational structures actually to pandas as a first-class citizen to be able to do it in a way that's scalable. And I mean scalable in terms of developer time, really. The ability to add things without doing a whole lot of work. So that's what we did. We now have a format, and we'll go through this in a little bit, giving the example of how we added integer NA support to pandas. So this is basically two things. It's a dtype. So we'll call it real data types. Just like NumPy has float 64s, now we have a real dtype for datetimes with time zones. We have a real dtype for categoricals. It's actually parameterized. And this allows one big thing. It allows a complete decoupling of the storage format and how we deal with it in pandas. So no longer are we forced to wrap things in NumPy object arrays. We can actually have just an interface to talk to some opaque object. And so I'm going to show a couple of use cases of how this matters and what it gets for you. So when the 24 release comes out, which should be hopefully within a month or so, this has been a long release cycle, maybe 4 or 5 months already. We're going to have the types that we had before, datetime with time zones, intervals, categoricals, and periods, except these are going to be recast into our new extension array types. Also, we just merged, we have a first-class sparse type now. Now, this is an interesting, you could have a whole talk on sparse itself. Pandas has a, we'll call it a weird sparse format that's sort of its own, and we may eventually adopt another format, but it's now a first-class type. And then, of course, we added integer NA support as a first-class type. So here's two little examples, categoricals on the left here, where we want to represent a type that has many values but not so many uniques. A lot of folks use it nowadays to save memory, actually, but this is a real thing. If you use statistics at all, think of this as a factor type. And then I'm going to show an example also. I'm not going to actually show categoricals, but I'm going to show a real example of how to do unit support. And this has been a long time also missing feature of really lots of packages. So external arrays already exist in the wild, actually. As I say, and I'm going to go through this example in a little bit, CyberPandas was the original motivating use case for this, followed closely by GeoPandas. And these are two external data types. They're in separate repos. They have no dependence. They have a dependency on pandas, but pandas doesn't even know about these at all. Doesn't care, actually. There's an effort underway. It's a little bit experimental at this point. It's called Fletcher arrays. It's actually backing an extension array with a PyArrow array itself. And this is an interesting development for the future. We're watching it pretty closely. It's done by one of the PyArrow developers, actually. And then I'm going to go through an example of PyInt. This is one of the unit libraries. I'm going to show you how to do that. I also listed decimal and JSON support up top. We actually implement these in pandas. So you get these sort of for free. So now you can hold decimals in your series very cheaply, actually, and do operations on them as if they're first-class objects. So let me just show you, and then it'll become clear. So this is the repo. All the examples are here, and let me go to them. Let's see, exits. Okay. So this demo, this talk is a lot of show and tell, actually. Pandas is one of these funny packages. I don't have any fancy graphs for you, but I have a lot of show and tell. Let's see. Okay. Can I not zoom in a little bit here? Can you see that? Okay. So I'm just indicating that this requires, Pandas master at this point, and this will be released pretty soon in Pandas 24. So Pandas, integer NA, why do we actually care about this? You care because of this. So this is probably the bane of all people, where you have an integer series that's int64, and then it suddenly turns into float64. And that's a little bit unnerving. This is solely due to the way we're storing these. We can't store integers, or we don't have an NA value for integers. In fact, I considered doing this a few years ago, actually, using a sentinel value, similar to how we do this for datetime 64s. And it would have worked, actually. Just we never did it. But it's not super extensible to do that. Doing this for int64 is one thing, but when you have int8, what do you use as your sentinel value? I can pick one, but that may be a problem in the real world. So this is just a better solution. So what we can do now is this. So a thing to note, the dtype is actually a capitalized version of the dtype. It's a little bit weird. So this is actually an opt-in extension, and it's not going to break any existing code. Nothing will be force converted to this. At some point, I'm going to turn it on, but not yet. Because the problem is, I haven't even turned on Pandas test suite, and I know we're going to have like 1,000 breaking tests if I do that. But the point is, it is opt-in for now. You can use all your favorite int types and uint types. They just have a capitalized letter. It seems a little bit odd, but it's sort of convenient. And the point is, it gives you an object underlying this, and we're going to show you how it looks. And it preserves. It prints out nans just because people are used to that. But it preserves the ints. So you can do all kinds of your favorite things with this. You can do sums, and you get back scalars. But you can hold it in data frames. And this is also, this is where it becomes pretty useful. So we create a data frame here with 2 columns, So we're actually holding a regular int column or a regular pandas column, and we're holding a new extension array column here. They look and feel very similar. And that's on purpose, actually. So you can do lots of things with these. You can group by them. Actually, here we're grouping by the int column, and then we're going to sum and create the sum of the extension array column. And we have, this is just a regular grouping operation. I haven't done anything special here. We get back a regular grouped index. I'm going to show the comparison in a second. But am I right here? There's a bug here. I just filed an issue on the tracker for it. The issue is that this return type should actually be int64 here with a capital I. Okay? So there's still bugs in this. This is another reason not to release this in the wild as like a fully baked feature. And they're very subtle sometimes. The protocols inside pandas are not all updated. We haven't hit all the edge cases yet, so that's part of the reason for putting this as an optional add-on feature. So that's the bug. So, but there's also some other limitations. So if I do the reverse operation where I group by the extension array int column and do the sum, I actually get back this object index. It's kind of weird. Because remember, when you group by something, you get the index of the grouper as you get the values of the index that are the uniques as your index. And this is right now a limitation. We don't actually have an extension array index itself. There's a PR up to put one in, but we just don't have it yet. So there's a lot of features of pandas which we need to build out to really fully accept extension arrays as first-class citizens. But here is what everybody wants, right? We have our data frame, we add 1 to it, and we preserve dtypes. Okay, that's great. But more interestingly now is we're going to assign some nans. And if you look at, I just assigned a nan to the second column here, or the second row 2. Oh, sorry. And then I do a fill in A, and we have preservation of dtypes. And this is something that you would expect would just work. Unfortunately, with our implementation of NumPy dtypes, it doesn't work for regular columns, for regular ints. So we have forced conversion. Here it preserves it. Okay. Indexing works exactly as you'd expect. So interestingly enough, extension arrays don't even care about this too much. They just need really simple indexing. So most operations are simply preserved. Now, how do we actually implement this array? Well, it's actually really simple. So take our series. It's just, so we have these first-class types, and they're called arrays. In some sense, these are drop-in replacements for NumPy arrays. That's the goal, actually. They may not be full drop-ins. We're not going to support the full panoply of methods that NumPy arrays do. They have way too many methods. But for the most part, they'll just simply work. Okay? And the implementation actually is really simple. It's just data, and it's actually two NumPy arrays is what it is. It's a mask and the data itself. That's actually, interesting enough, I fill it with ones, of all things. So, but the point here is the implementation is completely separate from the interface. You could actually do whatever you want here. In fact, one thing I think I'm going to do, this mask here is actually a NumPy array it's a Boolean array, but it actually takes up a little bit of space. We could actually represent this as a bit array. We don't actually need a full byte array, but okay, it works fine for now, and it doesn't add a huge amount of overhead. But this leads to an interesting question. How does this fundamentally change your view of data frames? And I had some conversations earlier today about this. So long story short, and this is not a discussion of data frame internals, but Pandas stores most data as two-dimensional arrays. So that seems natural, right? We have dtypes, so we store a list of two-dimensional arrays. And that seems okay at the outset until you start doing things like modifying part of those arrays or splitting them apart. Pandas, we call this the block manager. And this has been a long-time feature of Pandas. It was set up originally in 2008. And it works fantastic when you start with, say, NumPy arrays, 2D NumPy arrays, and you put them into a pandas constructor, there's 0 copy. It's great. But then when you start mixing in other dtypes and changing things, it's not so great. You end up with lots and lots of copies. So how does extension arrays differ in this? Well, it differs in a fundamental way here. So I'm creating another data frame here. I'm adding 2 more columns, another int column and another integer NA column. Ignore the warning. I'm just forcing what's called a consolidation here. I'm forcing the block manager to do its thing. It's kind of lazy on doing this anyway, so I'm just forcing something that should happen later. And not to go too much in the internals, but what you'll notice here is the float block here has been what's called consolidated. So we've taken those 2 1D float arrays and we've copied them into another one, a 2D one. But the extension arrays we haven't done anything with. So we haven't copied these. We've in fact taken the original arrays and left them like they are. So this actually offers quite a number of performance advantages in the fact that it's not that we don't copy them, we defer the copying to the extension array itself. So you can choose to copy, you could use views, you have a lot of power there. But with regular scalars, like with regular NumPy dtypes, we don't offer that possibility. We may at some point, but not yet. So the interface that we've defined is actually pretty simple. It looks almost like a series. You know, we have things like drop an A, and we have this routine called factorize, which is basically mapping things to numbers. We use this in grouping and all kinds of things. So we have a number of routines which you must define, like take. Some basic indexing operations. Things like is something an NA and unique. Once you define these, you instantly have an extension array. So it's pretty easy to do, actually. And I'm going to show you an example of someone who did it without any interference from us at all, which is kind of neat. Well, this should be on the next slide. But what doesn't work? Well, the 2 bugs I pointed out already. But one more. So you can, of course, take your data frame and write it to a CSV. I'm writing it to a string in this case. But reading it back is just, I guess the error is off the charts here. But it just doesn't work yet. And you know, this will be fixed. It's more of a matter of not everything works right now. Serializing these to other formats doesn't work yet, but it will. There's already been some effort, as an example, to make this work with Dask. You know, things like we support hashability of data frames, and that already works as an example. All right, I'm going to show you 2 more examples here. So this is the original motivating example. Let me go to the top here for why extension arrays were created. This is also a public library called CyberPandas. Say you want to store IP addresses. And I don't know, I'm sure there's people who, network people who want to do this. It's a pretty useful thing. But let me show you why it's useful. Well, once you have an array, and this is a fully first-class array type, you can define your own methods on it. And, to do various, kinds of operations which are endemic to that type. So you have really type-specific stuff. You also have the opportunity to define your own scalars. Now, in my previous example of pandas, with integer NA, my scalar was a NumPy scalar. It was actually, it could be a NumPy scalar or it could be a Python scalar. I didn't have to define a scalar. In this case, I do want to define a scalar because I want it to be imbued with certain properties as well. And then, of course, you can put these in series. And here's another interesting thing. Oh, that's not interesting. Here's the interesting thing. So everybody's seen what we call accessors. Things like when we do .dt or .cat or .str, these are methods which are type specific. So it will only work on that type, strings or categoricals or datetimes. So you can do this as well. You can define a method that will only show up on your type. Really pretty useful. You get tab completion. See if I can actually do that here. Yeah. Show it. And then, of course, you can put these with other types, just as we saw before. So these types are really our first class. Let me show you one final example here. So this is a library I only found out about because someone pinged me on their repo. This was Pyint. This is a, I don't know if you say it's Pint or maybe Pyint, I'm not sure. This is one of the, we'll call it, 3 different libraries for units out there. There's one called quantity, and there's another one called, I think, YPint or something like that. These are actually used a lot by the astronomy folks, but there's obviously a ton of other people who want to do this. Now, why do units matter? Units are a big deal because, we'll go back to the simple physics, force equals mass times acceleration, right? And if I don't know which column is which, you might get confused, you might lose the labels, so to speak. So we can, of course, label things. I mean, think about what pandas does fundamentally. It takes a NumPy array and slaps labels on there. This goes even one step further and adds a piece of metadata that's carried around on the labeled column that also knows how to do operations with other units of that type, or not necessarily of that type. Now, we already have some features like this in pandas itself. Example, when you take a time delta and you multiply by 2, well, we know how to do it. But we don't have real first-class metadata propagation. We have some mechanisms for it, but this adds it in a first-class way. And this was done completely in an external library. You need also master of Pyint. It may be released by now, I don't know. You need master of pandas, but soon both of these will be public. So example, you have some data and you've labeled what kind of unit it is. And here we actually see, so we're reading into a CSV, and then we're actually using some, we'll call it accessors that are actually defined on the data frame itself to basically turn these into, you notice the labels disappeared, and we'll see them reappear in a second. These now know what units they are. So these are all Pyint types. And of course, you can do operations on these. Now, the operations are solely determined by the type itself. It may raise in certain cases. Maybe it's wrong. Maybe these things are not implemented yet. But the point is, the type is solely in control of the operations here. Pandas doesn't know anything about this. We simply defer the operations to the type. So here, we're defining a new type, and it knows how to do this calculation here. And a similar type of, they decided to implement a conversion type, and you can convert to kilowatts here, and then get some nice pretty printing here. I don't know if you can see that too well. And of course, in our, well, I don't know what that slide was. Okay. So again, the implementation is a custom type and a custom array, and that's it. So you can define these. These are base classes in pandas, and you can go and create your own. And as I say, there's quite a number out there already. I expect more to be created because these really are useful and they're very, very lightweight. I think at some point we might actually completely take out all of our NumPy backed types and replace them with extension arrays. Maybe, we'll see. If some enterprising person wants to come into this, would be great. Let's see. Let me go back. I think that's my last slide. So these are the 3 extension types I did here, and I'll tweet these out at some point later. So that's it. Any questions?
Thank you. Great talk. Quick question. You mentioned the deferred copy. Is there like a copy on write idea, or did I get that wrong?
It's not that it's a copy on write idea. It's when I say, so if I have a series and I need to copy it, okay, you'll get a copy call in the interface. You could actually do something like take a view, and you can defer your own copy to when you have set item called on you, as an example. So the ability to do copy and write is possible now, but it's deferred to the extension array. No one's implemented this, but it's possible. Anybody else?
So what about extension arrays for strings? So you present them as object string. What about the STR?
Okay, so the question was, what about extension arrays for strings? So right now we have extension arrays for categoricals, and you can use them for strings. However, there's some limitations because the fact that they are categoricals, they follow categorical semantics, okay? So the answer is yes, there's a string type coming. And that will be think of it as almost a light wrapping of categoricals when we remove the restrictions. Okay? So we'll just automatically categorize things. We'll allow you to add strings to that set without blowing up. Okay? So the answer is it's not very hard to do that. There was also even a request I heard from someone else to do fixed length strings. All of these things are possible and not a whole lot of work, and they can be done in an external library. If they were super useful, certainly we could consider bringing them into pandas proper itself.
All right. Jeff. Over here, Jeff. How do the integer arrays differ from like a masked array? Because they look very similar.
So from the external viewpoint, they look very similar, just as pandas internals look similar to a mask array. The answer is so if you're asking could mask arrays be used as an implementation, the answer is yes. Do they differ? No, not significantly. But they play nice with data frames. That's the main use case, to be very honest. So, any other questions? All right, that's it. If you have any more questions, I'll be outside.
Thank you so much, Jeff. Everybody give him a round of applause.